We thank everybody who interrupted me earlier this morning. Please keep it coming. So now we're moving on to a more technical and more practical side of things, which is how do we actually get these things running in VMD and MD. And the VMD, I will insist on the VMD side, which is, I think people are less aware of. So latecomers, I need to set them with my laser pointer. Yeah. I'm really, sorry for disturbing your conversation.
No. Yeah, let him do the talk.
I need a high-powered laser pointer. Yeah. All right. So we have our system really complicated. We need to, reduce it somehow. How do we define those collective variables? How do we analyze them? How do we pick them? How do we bias them in practice? So this is all done, with the help of a balding Italian guy, Giacomo Fiorin, who is my main collaborator on this software tool, the collective variables module. So the collective variables module is all about, implementing these collective variables-based calculations. And so it's usually, arbitrary dimension, and you can do many things. Actually, this is just a summary. I'm going to get to the gist of it. How do you do collective variable calculations? Well, suppose you want to do targeted molecular dynamics. To do a collective variable simulation, you need to define the variables and the biases. Biases are just really any algorithm that acts on the variables. And in this example, define a variable, I called it RMSD because I have no imagination whatsoever. It contains a single function, RMSD function, defined on a set of atoms that I'm picking based on some tag in the PDB file. I'm giving reference positions because RMSD is computed with respect to these. And then I'm adding a harmonic bias because targeted MD is just a harmonic bias that is moving towards lower values of the RMSD. So it's acting on this RMSD variable. The initial value, center of the bias is 5.3 because that's whatever it was at the beginning. The target is 0, so it's moving closer to 0 RMSD. It's doing that in this many steps. And the force constant is 100 of whatever the unit is. In this case, it's kcal per mole per angstrom squared. And there, this is the input I need to run this targeted MD example. So, in MD, there used to be a code for targeted MD, a code for steered MD, a code for geometric restraints. And all of these kind of, are covered by very slight variations on this kind of example. Now, okay, you want to run a Kohlvar's calculation. First step, getting the code. How do you get the code? Easiest way is, from the precompiled binaries. So just download recent version of NAMD or VMD, use Kohlvar's, profit. Simple enough. If you're not happy with that, or you want to compile your own version, you want to tinker with the code, you want a bleeding edge version. Actually, in NAMD's nightly builds, you get already pretty recent versions. But we have this source repository that people seem to like. I'm very happy they do. It's on GitHub. It always has the up-to-date code. Actually, various branches with different variants of the code. It has the up-to-date documentation. It has a regression test. It has an issue tracker, which we use a lot and few other people use, but feel free to use the issue tracker to report issues. We do rely on user feedback, although there's many channels to do that. Where can I find the documentation? So the Kohlvar's documentation is kind of big and intimidating. There is several options. So the NAMD and VMD user guides each have a Kohlvar's chapter, and they're also available separately, in a maybe more convenient HTML form at kohlvars.github.io. You'll find some more involved details in the publication, which is Multis 2013 paper. And then you'll find more information in the form of examples. So the ones we'll be talking about and using today. So if you have your laptops, actually, I encourage you to, if you haven't downloaded that stuff, to download it. Probably now, because we'll be, like, essentially the practical part of the session could start right now. I'd like to blend it with this talk. And then there's more advanced examples, typically, that are mentioned in the Colvars publication, and then others in this subdirectory of the main tree. So this is a separate repo, and this is a Colvars repo, but it has an example of directory. A third source of information, if you have a special situation that's not covered in the docs, or you have trouble finding your way around the docs, which admittedly are kind of large, is the mailing lists. So, both NAMD and BMD have these nice mailing list archives you can search. Actually, they're really well indexed. And on the NAMD mailing list in particular, but also in BMD, so you find a total of yesterday of 2,000 something results, so messages that mention cold bars. So the chances are that your issues could be covered there. If it's not there, don't hesitate to send a precise question, pick the right mailing list, of course, NAMD or BMD. Most of the conversation on cold bars has been happening on the NAMD list so far. That might change. Okay, so what does, any questions so far? Sources? Okay, what does that software do? Let's have a quick tour of features. So the idea of the Colvars module is to provide a collective variable modeling workflow. So not just one simulation, but really there's a whole process by which you can have a relevant simulation. So the one really important step is design of the Colvars. And the design of the Colvars, again, is fueled by the knowledge you have of your own system, whatever degree of freedom are important. Then implementing them, that's where I'm going to talk about how you can do that. There's many ways you can implement a certain function variables. So the Colvars provide a set of basis functions. I'm calling zeta here. In Colvars lingo, we call them components, or collective variable components, or CVC. That's their acronym in the code. And then you can combine them at runtime with polynomial combinations of this form. So you give each component a certain coefficient and a certain exponent, integer exponent, and then the Colvars do the rest. Or you can have custom functions that are combinations of these. And there's two ways of defining such custom functions, which I will describe. Once you have implemented them, you can do bias simulations in NAMD or in LAMMPS, or both. And then the biases will be, the algorithms we talked about. And then you can analyze the trajectory. Actually, that is, you could also analyze the trajectory of an unbiased simulation, of a simulation that doesn't have Colvars in it, but analyze it using Colvars just for analysis. We'll talk about that. That could be, so that means it could be the entry point of this whole cycle. You have some knowledge from somewhere else. I need to complete this diagram. You have some simulations, or you have a set of structures, different states, maybe. You can analyze them within BMD in terms of Colvars, play with different Colvars, and once you have variables that you think are capturing whatever's interesting, then you can start running the simulations using those biases. So what kind of functions do we have at our disposal to begin with? Well, this is the set. It's just taken directly from the documentation. And so I've tried to classify them in different groups. So a bunch of functions based on distances, plane distances, vector distances, unit vectors, so just giving the direction of the vector between two groups. Some combination of distances that is actually mean distance, but it could be used to get the minimum distance or a form of minimum distance. Then there is these two kind of special components that are really, I'm calling raw data, because they just give either the list of pairwise distances between the atoms in two groups, or just the plain atomic Cartesian coordinates. So this is not a collective variable at all, it's just a set of Cartesian coordinates. Why would you want to use that? well, not directly as collective variables, but more as part of you make your own collective variable. So you would take this as input and write your own function of these, and then you'd get them. Thus, if you don't find what you're interested in the list, just take these coordinates. Maybe it's maybe it depends on absolute coordinates. So you want to use the Cartesian component. Maybe it's based on pairwise distances. So you can use distance pairs component, and that's a good start to build your own coordinate. Then there are a set of coordinates based on angles, some of which are useful for some restraint schemes for the binding for energy calculations. Maybe Chris will mention that again. I keep listing things you have to mention, Chris. I'm sorry, I'm putting things on your plate.
I'm taking good notes.
Then we have 3 components related to coordinations. The plane coordination number between 2 different sets of atoms. The self-coordination number, so number of pairs in contact within a group of atoms, and then a measure of hydrogen bonds. Then we have the very collective. Remember when I was talking about some collective variables are more collective than others? Well, these would be the more collective ones. So plain RMSD, then some variants are RMSD based. You can combine RMSDs in interesting ways. I'll come back to that later. There is this eigenvector, which might not be very well named. You can say that because I named it. And it's really the projection of atomic coordinates on a vector, any vector. Very often that will be an eigenvector coming from a PCA analysis or some form, or normal mode analysis. So it's often an eigenvector of some sort, but it's any vector you want. It could also be simply the difference vector between 2 structures. If you want to go from A to B, and you think the pathway is kind of linear, you can take structure A, structure B, take a difference in coordinates, and project whatever your atoms are on this, on this linear vector between those 2 states. And that could be a good coordinate in some cases. That's for you to decide. And then, radius of gyration, moments of inertia. Okay, then it's a bunch of more unusual coordinates, orientation-based. So these are all based on some measure of the overall rotation of a group of atoms, and I guess I'll come back to that in detail a bit later. And then 2 coordinates specific of protein structures. One of them is a measure of the alpha helix content. It's actually a combination of hydrogen bonds. And the other one is a dihedral principal component, which you might know of or not. It's actually something that was developed in the group of Gerhard Stock. And it's a way to analyze protein dynamics. It's like principal component analysis, but in the space of dihedral angles, like backbone dihedral angles. And that takes a little bit of extra precautions as opposed to regular linear PCA, but it's actually quite useful, especially to describe very flexible peptide chains. So for instance, if I wanted to go back to the decaalanine example, and the region where the decaalanine is extremely flexible, so it takes all these different, compact conformations. If I wanted to come back to that now and describe it properly and sample it well, I would certainly use this coordinate, like 3 of these, and that would work better. Although, ideally, you probably need 5 of these, and then it gets complicated to sample in 5 dimensions. I've never tried. If you try it, let me know. Okay, so these are, the basis functions. Then, if you don't find what you like here, we have, this is like write your own call bar, WYUC. And the easiest way to do that is probably to write your function with the lepton library. So the way this works, suppose you have these components, you have 2 distances, one of them you call x and the other you call r. Oh, no, sorry. One distance called x, and this is distance vector. So this is one component, just 3 components. You can actually combine seamlessly like scalar and vector quantities, because once you define r and you're saying I'm running a custom function of these, well, you can use this as variable x, and r will be split into its 3 components, just named r1, r2, r3. So then you can write one function. So it's a scalar number, and it's x minus the first component of the other one. So it's like x minus the other x, because x is this. And then the other one is cosine one plus the sum of whatever. It's like extremely random. The bottom line is because I have two lines here, I'm defining a variable that is a vector, a 2 vector, and it's a function of this one plus those, so it's a 2 vector that's a function of the 4 vector. And that's it, and then I can apply bias to this, variable, my variable, and of course the center is also a 2 vector, force constant, and that's it. That's right. So this library was written by Peter Eastman, and it's from OpenMM. That's correct. It's actually a subset of the features of the Lepton library because one of the nice things in Lepton is that it will do just-in-time compilation and it will write optimized CUDA and OpenCL code based on your function, like on the fly. But we're not using it here because we don't expect this to be really a performance bottleneck. So it's not like we're writing our non-bounded kernels in Lepton, which is what you could do in OpenMM. So we didn't go all the way, we just imported this like more basic parts of Lepton.
But you could do without it, right?
Without what? Sorry?
Without Lepton.
So you can also
infrastructure to do it without Lepton.
Yeah, well, that's using scripts.
Using scripts.
That's my next slide.
Okay, so.
Now you're putting things on my plate. So were there any questions with regard to that? It's clear. So another option, which is more flexible than Lepton, a bit more cumbersome to write. It's not as easy as just writing a expression, but you can do way more stuff, is to write your own TCL script. If you like TCL, and if you don't like it, you'd better like it because...
What was the previous link?
Work on it.
What was the previous link?
So actually, it's not really... So you could call it Lepton language. It's not really much of a language. It's just plain like mathematical language. There's not much. You write it as you would write mathematics on in a calculator.
Because the syntax of this is very similar to TCL.
So I'm sorry. The syntax. So this is the Colvar's input syntax, right? The only thing that is Lepton syntax are the red strings here. Right. Okay. This is just a Colvar's config file, custom function. Whatever string you provide to custom function, this is parsed by Lepton. And what the Colvar's does for you is define these variables x, r1, r2, r3 based on your variables, and it provides Lepton with the values of these. So the reason why this is really efficient is that what Lepton does is it will compile these into an evaluation tree, and then it will have essentially pointers like memory references to each of these. So that is compiled once and for all, and what Colvar's does is just set the right values in memory at those locations, and then call the evaluation function and get the result. And the other thing that Lepton does, which is nice, is it will compute the gradient of these as well. So here I'm just providing the function, but to apply a force, you need the derivatives. Lepton will do a kind of algorithmic derivation or differentiation. So you don't have to worry about the gradients.
Like formal.
Yeah, formal. Yeah, because once you have the evaluation tree for this expression, actually, you can there's an algorithm that will derive the evaluation tree for the gradient based on that. It's not very complicated, but it's very neat. All right. So then if you want to something more that you can't do directly with Lepton, so here this is two different things. So this blue text, this is your collective variables input. So you define a Colvar, you name it like this. You define here. I'm defining two RMSD components, and then the way they are combined will be, you'll have these slides. The way they are combined will be through a scripted function that I'm calling pathCV, and the pathCV implements these path collective variables. That's something that well, you heard about these, right? Because you talked about the string method. Yes. So you heard about these, but maybe you didn't see the under the hood. Good. So you heard about these, and then this is something that actually, Chris and I wrote together to calculate these things. Or actually, really, Chris wrote this version, and then I worked on optimizing the performance. We'll see that later. So
you have to understand, I wrote a crappy piece of code, and he fixed it.
That's
It's true.
You wrote the code that literally evaluates this, which is the published expression.
I'm not ashamed to say it.
There's no. Okay, well. So
Actually, you guys did a very nice job. Because, I mean, are you going to explain this?
Yes.
Math?
yes, yeah. So here we're promising. What we're doing here is we're promising call vars that will provide functions like procedures actually implemented in TCL that will compute this coordinate. So this is called the chaotic path CV, fair enough. And the other one is called the chaotic path CV gradient. Should be self-explanatory, right? So the arguments here will be the value of these components. So this will get two arguments, which are the values of these two RMSDs. And then based on this, we evaluate this sum. And then the other one, we evaluate the gradient. We return that to call vars, and call vars does its thing. So the difference, there's two differences with lepton. One of them is we have to compute the gradient explicitly. So this code is the derivative of that code, essentially. But the plus side is we could do really anything here. And one thing we could do is make it more efficient. Why? Because here, you have a string, you have a number of images, and this sum is a sum over the RMSDs with respect to all of the images. And computing the RMSD with respect to each image will mean that you do a least squares fit of your current positions with respect to that image, and then compute distance, and then repeat that. So that would mean that at every single time step, if you have 100 images, every time step you'll do 100 least squares fits, and that will cost you a lot of time. But because of this exponential thing, the goal of these exponentials here is you really want to know where you are along the string or along the pathway. So you really want to know which images you are closest to. And the images that you're not close to contribute negligible amount to that sum because of this exponential. Okay? So really, you're computing a lot of RMSDs that are big and that you're going to put into this exponential, and that will give you 0. You're wasting a lot of time. So what you want to do really is to compute only the RMSD to those few images that are nearby. And so, right, all images, that's what I said. So in a modified version, but it's longer, so I didn't put it on screen, of this script, what it does is it does a kind of neighbor list, actually. So it computes first all of the RMSDs, and then it decides that it's really far away from many of these images. So it just keeps a list of those that are closer. And then it uses a set of flags. So there's this command, or the CBC flags, that was implemented more or less for the occasion. So the script can turn on and off the computation of whatever components that are not useful. So the script would just say, well, for the next time steps, don't compute all of these, just compute these few here that are close to me. And then it will keep running. And then once in a while, after a cycle, it will do a refresh. So it will ask for all of the values, then decide which ones are close enough, and then disable again those that are too far. So that will drastically improve the performance of this code, being able to turn on and off things. So that's one really, something you couldn't do in lepton, because lepton doesn't plug in to call vars with the same flexibility that you can do with TCL script. The TCL interface is kind of rich. So you could also imagine, I don't know, here you could turn on and off components, but you could also say, if you find something interesting, this bias could create, or this is a call var. This could create a new call var. Or this could say, oh, I'm not interested anymore. You could, this call var could delete itself. Let me see, you might get a seg fault, but I need to check. But you could imagine a call var that decides it's not valid anymore, creates a new copy of itself, different, and deletes itself. So like a self-updating variable. That's totally in the realm of what you could do with scripted variables. You could also do a variable that acts on its own biases. So suppose this variable is under a harmonic bias, but it decides that the harmonic bias is not the right one anymore. It could change it, on the fly. As soon as you're scripting stuff, the sky's the limit.
I have a question. So you have an argument for those functions.
Yes.
Which arguments are you receiving? Does NetD provide any automatic arguments?
No, so these are sent by call vars when you're calling this callback, and these are the values of the components. So here, in this case, there's two RMSD components, so this will get two RMSDs. Okay, two values of the RMSD, and based on this, it will return the value of the of this app system. and the gradient will receive the same. Yeah. So one thing that this does as well, I think, is that, does it reuse it? Yeah.
So you have an end there. Where do you use it?
Here. That depends, because, yeah, because
Okay.
1 over p, like
Sure.
p is the number of images, pretty much. So
Okay.
it's 1 over p minus 1.
Then you
And
go
it's-
for each over the arguments itself.
Exactly.
Okay.
Okay. So one type of components that is, I think, unique to cold vars is all these orientation. Yes.
One thing that's just a comment in class, that's with this kind of function, you need to use kind of constraint.
That's right. If you want to do ABF, these functions will not provide all the extra bells and whistles that ABF needs, but you can use EABF. Good point. Which is why I'm sure when you do, you could do. Do you do ABF after a string method, like ABF on a string, or EABF? Yeah, for EABF. Okay. So these self-body rotations, what do I call self-body rotations? They're essentially rigid body rotations when the rigid body is not rigid. So, I didn't know of an existing phrase in the literature. So why is that? A rigid body rotation is something pretty clearly defined. But what happens if you have like a protein that moves around? It has this global rotation, but at the same time it's flexible, right? So how do you define this rotation in a very unambiguous way? One option that's been used was the principal axis of inertia, but that's not always robust, depending on the geometry we're looking at and depending on how much deformation the protein undergoes. And I think, I haven't seen a method that is more robust than this actually, which is saying, well, I have my protein started in this orientation and then moved around and then it shifted conformation as well. How do I quantify its new orientation, or its relative orientation? Well, the best way to quantify it is to do a least squares fit of this protein onto its starting position, and whatever the optimal rotation is to superimpose these two is my global rotation. Right. So this is the idea. So what we're doing is we have the current coordinates x, and x0 would be my reference coordinates. R is the optimal rotation, so I minimize the square distance between the rotated coordinates and the initial coordinates. And R is itself R would be the coordinate I'm watching, so I'm watching the rotation itself. So in practice, R would be expressed as a quaternion. It's like an object with it's like a vector of 4 coordinates. Although there's only 3 degrees of freedom, or there's 3 rotational degrees of freedom, so the 4 coordinates actually have this constraint that they're normalized. So there is only 3 actual degrees of freedom. And then once you have that, so that is actually this coordinate is called orientation in the cold vars lingo. And then based on that, you could decompose that rotation into 2 different rotations. Suppose if you have a system with a preferred axis, imagine you have a transmembrane protein. So you have the membrane normal, which is your specific preferred axis. You can decompose this rotation into how much the object rotates around that axis and how much it rotates around, well, any other axis, essentially, orthogonal to that axis. So this decomposition, so if you call these spin motion and tilt motion, you get 2 angles. So actually, they're not implemented exactly the same way for mathematical reasons. So one component is called spin angle, and it goes from it has a full 360-degree range. And the other one is called tilt. It's not exactly the angle, it's actually the cosine of the angle, because it's better behaved. It's like 0 to 180. So this is the angle, and the spin angle is the angle of the tilt, the cosine of the tilt angle. Then, based on a similar approach to that, another really specific thing to cold vars is that you can use local moving frames of reference. So the way this works is all coordinates internally are based on atom groups. And there is these two options, center reference and rotate reference, that will result in the atom group not providing its plain like lab frame of reference coordinates, but returning translated and rotated coordinates based on some least squares fit again. And so this least squares fit will amount to working in a different frame of reference, moving frame of reference. So imagine when you do a standard RMSD, that mechanism is already happening. So you have RMSD of your protein has this global motion, translation, rotation, plus deformation. What you do is implicitly these flags are enabled internally, and so instead of returning these, a raw coordinate, the atom group does an optimal translation and rotation, and then it returns these fitted coordinates, and then the RMSD function just has to compute the plane deviation, right? Because the deviation is already minimized. But so that's done internally when you do plane RMSD, but you can control that explicitly. So you can, if you can use a different coordinate and ask for this to happen. So you could imagine that you want to see, you have like a small molecule diffusing around the protein. So it's starting from a cavity and it diffuses along the channel or between different cavities. You could watch the distance vector from some starting point to wherever you are. So you want to see the position of the small molecule with respect to the protein. Well, you can have this distance vector. The problem is if the protein itself moves, well, just using these flags, you can ask for the distance vector, so the position of the ligand, after fitting the protein coordinates. So essentially, you're looking at the ligand's position in the frame of reference tied to the protein. And that will still be calculated in a robust way, even though the protein itself is flexible. So we'll still cancel overall motion of the protein. Yep.
Was this like some variant of Capsch's algorithm?
Yeah, so we're not using Capsch's algorithm because we're using the quaternion-based variant, which is a paper from the Kendall group, I think. It's cited in the Goldbar's paper, or I can find you the reference. The first author's name, Greek name. And others, and I think it's a little more robust than the Capsch algorithm, actually. But it gives the same final answer. All right, so yeah. So this is kind of the more probably conceptually involved things that can happen with Goldbars. So let's look at one example. We want to describe relative rotation in this dimer of helices, the rotation of one helix with respect to the full dimer. So we want something that is sensitive to rotation of one helix with respect to the other, but insensitive to overall rotation of the dimer. So what we need to do for that is, first, we want to remove overall rotation of the dimer, so we do this fit. So there's optimal rotation for AB that minimizes, that fits current coordinates of dimer onto initial coordinates of dimer. And then we want to fit one of the helices with respect to its original location, original orientation in the dimer. And that rotation, so RA, so R tilde AB would be the optimal rotation for AB. And then we get this rotation A, so that is relative rotation of helix A within the dimer. Then that in turn can be split into the spin and tilt version. So we get two internal rotation angles. So we know how much helix A has rotated within the dimer. And we can apply biases on that or do differential calculations on that. And that's just, this is going to be a longish input. But I think there is an example in the examples folder that has something like that. So the keyword for these, essentially when you're computing a coordinate and you're fitting the coordinates of another group, the important keyword is fitting group. So you're defining another group of atoms as the to define the frame of reference essentially that you're considering that group. When you're doing the standard RMSD, so if I'm looking at RMSD of my protein, the protein, like the group for which I'm computing RMSD, is the fitting group itself. But you know, so another example is actually RMSD based. It's a more recent example. So it's one way to determine the deviation of the ligand from a given binding pose in a binding site. And it's really, so we call that distance to bound configuration, DBC. And it's the ligand, the RMSD of ligand coordinates computed in the receptor's frame of reference. So what it does is it does capture the ligand position, orientation, and conformation. And it is independent of the receptor's position, orientation, and conformation. So all these the position and orientation of the ligand are computed always, independent of the inner frame of reference of the receptor. And so we've used that recently with my collaborator, Reg Brannigan, to compute absolute binding affinities of cholesterol to crystallographic sites on the surface of GPCRs. Yes.
When you're looking at that reference structure for these RMSD calculations, is there, I've seen papers that will sometimes recommend an average, using the average as the reference structure. Some just recommend using the first frame, first snapshot in an equilibrium simulation. Do you have any recommendations?
So it depends what you're trying to, so if you're trying to quantify deviation, right, like if you're trying to quantify like time evolution of a simulation to see how it deviates. I'm not sure I have a well-defined policy for that. I would say,
Doesn't matter.
well, I guess the different measures will give you different types of information, right? I mean, first frame will tell you how you get from the first frame. Problem with the first frame is that if you deviate a lot in a short time, after a while, once RMSD values get high enough, they get way less sensitive. So, once you go to high RMSD, really the RMSD won't tell you anything. So things could start happening that will not be captured by the RMSD. It kind of saturates at some point once you're far enough from the sun point. So that kind of argues in favor of using average or maybe the center of, I would say the most informative thing to do would be to cluster a trajectory and compute RMSD with respect to the centers of different clusters, for instance. So you could see it possibly switching from one cluster to another or something like that. It's much richer. Not that I've ever done it, but now that you're asking.
If I may comment, bear in mind that average structure doesn't exist.
Yeah,
So it's not physically correct. What it was saying that you compute the closest structure to some reference that you want, a cluster or any confirmation that you are more interested in, will be more correct than actually use pure average structure. That is just a construct that computes the average coordinates.
Yeah, doesn't represent much. Yeah. So this average, especially like linear averages of things that are not really vary linearly. I mean, it's a classic example of the average person of in this room, right? Who has like 1.4 testicles and all sorts of interesting characteristics. So not very important. What?
Especially the example that you gave.
In this example, you could start clustering people in this room using different characteristics and then judging the deviation of individual with respect to different clusters. Okay. Any questions on this? Yes.
How well do you perform from trying this?
We have we perform extremely well because no one else has this information. We're the only ones who have it, so we're like infinitely better than any other estimate, which don't exist. That's not entirely true. There's one NMR paper that studies binding to the beta 2 adrenergic receptor, but the only thing they can say is that there is at least they do see one high affinity sub-nanomolar binding site, which actually is pretty bad to begin with, because what does sub-nanomolar means? Like, what is the volume concentration of cholesterol? Like, if you're using like a water-based volume concentration of cholesterol, where cholesterol is barely soluble in water. So, you know, this is like the only estimates we found were not clearly like usable enough to be compared to what we got. So that's the thing. It's pretty common, I found, in simulations where you have this extreme high resolution, and all the experiments you find, you know, suffer from the resolution limits of experiments. So you may or may not have quantitative comparison.
But at least you can get like first one, this one of it, the second one.
Right. So what we do
You have
see.
3 scales.
So yeah, if you will, all of these are crystallographic sites. So we do predict that these all have some affinity for cholesterol. You know, I guess it's better than nothing. One thing I suppose could be a negative control. We could build decoys like other sites where we put cholesterol could get affinities, and we could find crystallographic sites to have much larger affinities than the decoy sites. That would be a good test. I'm not really, I'm not going to put in all the effort right now, but I'm glad you're not our referee. Anything else on these like local frames of reference, which is by far the weirdest stuff in here? So if you're happy with local frames of reference, we'll be happy with the rest. Good. So one thing you can do to save time is not compute the cold bars all the time. We already do that. You know, most NAMD simulations will be multiple time step. We'll consider electrostatic forces, like long range electrostatic forces and slow forces. It'll be like 2 or 4 time steps. And typically the collective variables are also slow forces. I mean, the forces on them are also slow forces. And then there's this framework that was defined by the group of Giovanni Bussi, and very nicely illustrated by the group of Giovanni Bussi. I'm not claiming any copyright on this artwork. So based on that, you can compute cold bars that are really cold for any time. So there's this, I think it's time step factor would be the keyword you add to your cold bar, and then it will only be computed every so many time steps. And if you have an expensive variable, that will save you a lot of time. And then the biases, in principle, the biases they're written so that they play nicely with that. And then the forces you add to your cold bars will also be, we need to have the same effect, so they'll be sent as an impulse-based method, as in the RESPA. So basically what you do is if you apply a given force, but you only update it every 4 time steps, then you're going to apply that force once, multiply by 4, and then no force for 3 time steps. And the next time step, you'll apply a single impulse for the whole duration of the cycle, which is already what is done for the other slow forces. And then if you have the extended Lagrangian, so you have this extra in your lambda coordinate, then the lambda coordinate will actually be explicitly course time dynamics, because the lambda has its own little integrator, and so the time step for that integrator will be your long time step, like your slow time for the cold bar. So that was everything you can do, or a lot of things you can do with the cold bars themselves. Now, what about the biases? I'm not
sure in this area, the cold bar. Can you say something about this?
That's actually, I'm supposed to come back to that later. Maybe I'll come back to it later. Thank you for reminding me. Somehow that's not what my talk going on. Yeah.
Just have a question on the multi-time step cold bars. Is it possible to define a cold bar dependent on a value of third cold bar? So you depend on the value of the other cold bar?
So not explicitly, but you have scripts, and with scripts you can do everything, right?
Of course.
So if you write a scripted cold bar, nothing prevents you from calling the scripting interface and requesting the value of the second cold bar. Okay.
Even on a multi-time.
Well, if you write a script, then it's up to you to do things properly, right? And to know when to query it and when not to query it. So if you query it, if you have a multiple time step cold bar, and you query it between its updates, you'll get a stale value.
Okay. So you keep the
Yeah,
it can still store global variables.
That's right. It's stored in
memory.
memory. The stale value is stored in memory. So then that's up to you to use it properly.
Okay.
All right. So then biases. Well, and I've talked a lot about some of the biases you can do. Like we've talked about harmonic, whatever. They're not the core of my subject. One thing I want to tell you about is what if you don't find the bias that you would like to run. You have your own little algorithm that you really like to try out, prototype maybe. Well, you can do that again with scripts. So this is the WYOB version. And this is just one example. As always, you just provide a TCL script. You provide this, trademark name, cold bar forces, and then this gets called every time step. You request it for the time step number, and then you do whatever you want. You call this value, this subcommand add force, which will add any force you want to any cold bar you want. And then again, the sky's the limit. So in this example here, I implemented a little bias sampling algorithm called adiabatic bias MD, which is an interesting way actually to, if you want to really go through a range of the coordinate rapidly, but not pushing too hard on the coordinate. And it's really more like you're just exploiting fluctuations of the coordinates, and you have a ratchet. So it's like essentially having a wall that will follow your coordinates, and whenever the coordinate fluctuates and moves a little bit forward, the wall follows it, and then it can't go backward too much. It's not actually a hard wall, it's a harmonic potential, or like half a harmonic potential. And then you just wait for the coordinate to fluctuate again, like to move to inch forward, and then the wall creeps forward and pushes it. And so this is pretty good at exploring rapidly a range of coordinates while adding a limited amount of non-equilibrium work. So I would say it's probably, I would call it a better method than steered MD for quickly exploring a range of coordinates. Actually, I wish I had heard of this method earlier. Somehow it wasn't on my radar. Yes?
So this would be a good idea, kind of like, basically, if you wanted to test a bunch of different reaction coordinates, I could use this to figure out whether like certain ones are more reasonable than others before.
Yeah, that's right. Okay. Or if you want to, or you know what coordinate you want to use, or you're kind of confident you have a coordinate that you think is good, but you don't know what other things could happen along the way. Instead of having a long adaptive, like simulation, you run this one quick run to like sweep through the coordinate, and maybe you have unforeseen events happening, and you'll revise your choices.
And I could just maybe increase the dimensionality by
right, or maybe pick a different coordinate, or maybe you'll see another degree of freedom that gets involved that you don't want to change. So maybe you add a restraint on that degree of freedom to separate the problems, something like that. Or maybe you'll find this so complicated that you'll just switch to another problem altogether. So how is this implemented? So it's entirely, it's not a very complicated process, but it's still a completely new bias. We have nothing of the sort. So what this does, first thing is you have to initialize this. So the thing is you have to follow what I call here the high water mark, the highest value of the coordinate has reached in the history of the simulation. So you initialize it with the initial value of this cold bar, $CB call that max, and then at a given time step, let's take the current value. If the current value is higher than maximum, then as long as I'm not, so X max would be the upper end of the range you want to cover. Like you don't want to go all the way to plus infinity and destroy it. So if we're higher than the current high water mark, but lower than maximum, then we increase the high water mark. And if it's not higher, then the coordinate is falling backward and is pushing into the wall. Then we add a biasing force that is just this harmonic potential. So some force constant times the difference between the wall position and the variable. And that's it. So this is like 13 lines of TCL, and I have an entirely new biasing method time-dependent bias. Yes.
The specific NAMD keywords to use in Tickle, that's in the tutorials. Is that right?
That's in, well, or that's at least in the, scripted, there is in the reference, in the doc manual, there is a scripted biases section that you'll find. And then this is, what's the word? I forgot exactly. Scripted cold run forces, something like that. There is a keyword. It should be easy to find in the doc if you're looking specifically for that. But I understand that, of course, unless you've heard of it in a talk like this, if you don't know that it's there, you might not stumble upon it. Any other questions on these scripted biases?
Do you have a Python equation?
There is, so you can kind of cheat, and there is this very minimal Python support. So you could essentially you could write a minimal version of that will call some Python to do the calculations, and then send it back. So yes, if you don't have to do your math in TCL if you don't want to, but the interface provided for this is TCL. It could be a very thin wrapper around the Python script.
But you just have to make sure that you have access to that Python version in the place that you are running.
Right.
So NAMD has to be able to execute that Python.
Right. And then these ships with the, so actually, wait, is it built into, the NAMD build has to have the Python interpreter.
It has a Python wrapper, if I'm not wrong.
Yeah. I don't use that very much. If my colleague Giacomo was here, he could tell you more about the Python-y things.
So if I wanted to include the calculation in there, I basically just have to make sure that that's not slowing the performance down. I just have the time.
That's right. So this is very, the algorithm here is extremely lightweight. So it will be, unless you are simulating a trivial system, like this test, like acetone and vacuum system. If you're running a protein simulation, you won't see the difference. Okay? This is so small. I would say most biasing algorithms are like that, but some will require some expensive math. And then there is a bunch of options you could do. One thing you could do that's pretty easy in TCL actually is to write a like C or C++ code that does the heavy lifting, heavy computation. And you can compute that as a shared object. You can do load. TCL has this load command that will load a shared object file, and you can just call, a TCL prop implemented in C or C++ or whatever, Fortran. Yeah.
Does that same feature exist with Java, or only for C and C++?
I don't think there is, because you need the Java VM somewhere. I've no idea. I wouldn't think so.
You said that was a shared proc.
Yeah, so it's a shared app. So you have to expose, there's a little TCL API. If you want an example of that, you'll find some on my GitHub repo. Okay. So it's like Hénin on GitHub. And there is two different, I think I have two different projects that use that feature. One is QWrap, which is this wrapping thing for VMD, right? That's just loaded as a shared object. And the other one is VecExp, which is like implementing the vector, like a vector calculator. So that's actually very close to, you might use that VecExp as is in a cold bars bias. Yeah, actually, if you want just to deal with vector data. Or you can modify it to suit the need. All right. So that's all I would say about biases, because we've talked about algorithms already. And then let's move on to the other side of things, not the simulation side, but the analysis side and design side. And then we are switching from NAMD to VMD. So there's this new thing in VMD. So for a long while, the cold bars has been built into VMD at the binary level, and we've had this scripting interface. But the problem which is very powerful, but not very convenient to use. You don't want to sit at the VMD console and write TCL commands to inspect your cold bar values and stuff. So we had a few scripts that take advantage of this. Like there was a script to plot the trajectory of the variables. There was a script to visualize the value in real time on screen. But as of very recently, I'm still working on it actually. There is this new graphical interface that lets you visualize your code bars directly in VMD. So I call that the code bars dashboard. And really, because it's kind of work in progress, I encourage you to get the up-to-date version from the GitHub repo. So actually, maybe I should show you exactly how it works. So if you find it, no. Okay, so just need to navigate to the version, navigate to the branch dashboard, and then it's in VMD scripts. VMD scripts, and you've got it. Code bar, CV dashboard, and then you get, the raw version. Download this, load this into VMD, and then let's give it a try. Let's see. Place. Yes. Okay. I'm just firing up the VMD session here.
You did try this before.
Nope. Okay. Did not. You mean I should be improvising?
I mean, that's what's.
Okay, well, it's, you know what? I'm not the best art. It's the wrong version of the thing. Oh. But I know I have it somewhere.
And you know that it works.
And I know it works. I know it works for sure. Yes. I know. I found it. Don't worry. I'm sure you're not worrying anyway.
No.
Okay. Here it is. Okay. So this is actually an example from the. You know what I should be doing? I should be mirroring the screen actually.
That will be easier.
It will be right here. So this is an example from the examples repo. So two leucine helices. Then I have this trajectory where they move with respect to each other. And I like to analyze this in terms of quality variables. So I'm just going to source the CV dashboard file. Now I have this window here. And I don't have any quality variables, so I'm going to load maybe a config file, open it, and now I have this, this table. I have 3 defined quality variables, and they have these values. One of them is the vector distance, so it's a 3 vector. The other is an orientation quaternion, and the third one is something I forgot what. Actually, there's just an example, really. And now if I animate my trajectory, I get these values updated in real time, so I know where I stand. in the along these clicky variables, I can, if they're really expensive and I just want to look at the trajectory, I can disable the track options, and now I can just animate, and then I can track again whenever I want. Okay, so this is cool. If I want to, suppose I want to look at something else, or inspect as what it is exactly, I double click on one of these, and I get an editor for the config file. So I see the config string for this particular variable. If I'm in doubt about some stuff, I can open the online docs here. Directly, I have a shortcut to the codec variables, to the atom group definitions, and to the callbar components. If I want to change the the type of, I could change the type of variable. Say instead of a distance, let's say I want a distance vector. Okay. So replace this distance with distance vec. Control S to save. And there's an error. What did I do? Of course, lower boundary, upper boundary. See, I get an error message. Let me try again to show you. Did this, and then I didn't realize that if I go from a scalar to a vector coordinate, then the keywords lower boundary and upper boundary don't apply because you can always have boundaries on a scalar. So what I do is I just remove these keywords, save again. Okay, it's happy. So now instead I have a vector coordinate. And so that's a way to explore. If I want to define a new coordinate, it's like new, it gives me just a skeleton. It's like a random, it gives you a random distance coordinate, but I can explore anything I want. Now, what if I want to plot the timeline for these? This, I get a plot for the 3 components of this vector. And then if I animate the trajectory, I have a little cursor here that shows me where I stand. And then, if I want to see details, I can use like a keyboard to zoom in. Okay, but then I can also use the keyword to navigate this. So I zoom in again. Okay, maybe there's not much happening here. And then if I'm interested in this event here, I can click on the trajectory, and it will take me to wherever it is, stuff's happening. And then again, like I'm not interested in this anymore, I can select another one. I can select all the variables, plot them. It's a little messy, but anyway. So yeah, that's pretty much it. That's pretty much an interactive way to explore a trajectory in Colvar space, and then change your Colvar definition. And until you're happy with them, then what you can do is save the config file. It asks you to save it to a new file, and then you can use that config file in a simulation. Okay, so I will definitely encourage you to explore this in the practical sessions. And then I will also, because it's really new, any feedback on this, on extensions to this that would be useful, I appreciate it. Okay, so that was the parenthesis on this. Did I just kill my thing? Yeah, I did. I'm not done with this. I think it was here. Okay. So that was the dashboard. Now, yeah, a few practical tricks that might be useful. So one thing that's you may or may not be aware of is that you can send your Colvar's input in multiple files or multiple strings, multiple PCs anyway. So you can either use this command in AMD only, Colvar's config, or the scripting command cvconfig file and read a file, or cvconfig and read a string. Reading a string is kind of useful if you're scripting, if you use TCL scripting, because this string could actually contain like TCL variables, so you can be building it as you go. So you can have a very, very flexible, scriptable configuration. And that also means that you can split your input files in different pieces. You could have like one file for every single variable, and so depending on the calculations, you can use different different sets of variables. And the other thing is the config, as we just saw, the config file for those variables can be written by the Colvar's dashboard. although you have to be careful that it does not handle biases, it will not write the config for biases or anything else that really restricted the variables. So that has to be in a separate file. And then depending on your workflow, if you want to define atom groups, you might take advantage of different ways to define them. One is the index file, and there's an example in this example folder. There's the write index file.tcl that will take, based on VMD selection, write an index file. Another thing that I didn't show you actually, but in the Computational dashboard is you can directly insert, you can insert lists of atom IDs from VMD selections. So if you have a VMD selection text that defines your atom group, just use that in the Computational dashboard. Another thing is if you're visually exploring the relevant atom groups, or you create representations in VMD with different groups, and then you want to use one of these represented groups as an atom group in the Colvars. Well, in the Colvars dashboard editor, there is a list of representations. You can just select one of these representations and insert those atoms into your Colvar. I think that will be even clearer when you're looking at that. And of course, a classic, but that's pretty effective in some cases, is to use PDB files with flags, and those flags can also be defined in VMD. VMD is probably the best tool to do that. So in any case, I would say like the workflow for a Colvar simulation should use VMD. I mean, VMD is a great tool for making it. If you've already used that, it's probably your experience. And then another concern is performance. We've talked about it, we've touched it on some occasions. So one problem is, so NAMD is highly parallelized, Colvars is only very partially parallelized, so it could be a bottleneck. Depends really what you're doing. One problem you could say is that depends how collective your variables are. But collective variable biases are intrinsically difficult to parallelize because a bias on collective variables is actually a long-range interaction, right? If you have an RMSE bias within a protein, it's actually an interaction between all the atoms in your protein. So it's adding the long-range interactions, but there's no, and it's a very collective. It's not pairwise, right? It's a long-range, many-body. That's right, many-body long-range interaction. So good luck with parallelizing that. So we've done what we could, but in practice. So first of all, when you try to optimize your Colvars, you should benchmark it with your own system and your own Colvars on your production hardware, because there's no predicting. I mean, otherwise you only have a faint idea what your optimizations do and whether they're necessary to begin with. So first thing to do is don't use any more atoms than necessary. So, classic is to be MSC and atom carbons only. The more atoms, the slower things will be. It's pretty sure. Variables that depend on standard mass of atom groups will scale much better because Colvars take advantage of NAMD's internals that will already do a reduction of centers of mass locally. So if you depend on centers of mass of atom groups, there will be no need to communicate the atom coordinates, but only the partial sums of atom coordinates. So you will find much better scale. If you have multiple Colvars or Colvars with multiple components or multiple biases, any of these, you have to make sure the SMP feature is enabled. And that's what Chris was talking about recently. So whether it's SMP, so this is like either symmetric multiprocessing or shared memory parallelism. I never know which one is the true acronym. But what it does is it parallelizes. So what Colvars does is if you run on multiple compute nodes, Colvars only runs on one node. So it doesn't use the inter-node communication. But within one node, you probably have many cores. And what this SMP feature does is it will distribute the work of computing different Colvars and different components and different biases onto whatever cores are available on node 0. So if you have a 32-core node and you have 32 Colvars, you'll gain a lot of time by making sure. So I didn't say enable the SMP feature, just make sure it's enabled because it should be enabled by default. So if you have a NAMD build that supports it, which is most NAMD builds, essentially a NAMD build that supports SMP. And if you didn't touch any of the cold options, it will try to enable it by default. And then there is somewhere in the output towards the beginning, the cold log file, you will see whether the SMP feature is on or off. But then, if you have a slow variable, you can use multiple time steps to reduce the frequency of the cold bar calculations. Don't go overboard with that. So I've done some tests with very, very low frequencies, and it seemed to run fine. But in theory, you're not supposed to go further than the longest time step of your MD integrator. So it's kind of be cautious with that, but definitely, running at full electrostatic frequency should be safe if you have, forces that are actually as smooth as long-range forces, electrostatic forces. And then, it's more involved, but if you don't need all your variables or all your components at all times, you could do like we did for PathCV and use a script that will set CVC flags on and off so that you turn on and off the variables you need. You can also have a script that will, again, create or delete cold bars on demand when they're needed. Another option. Kind of the extreme version. So that's most of the tricks. I don't know. Any question on these performance issues? Or not? Yeah.
As the cold bar dashboard ever experience, what would the performance be? Slow, faster?
Then what? Sorry,
So I was just thinking because I'm working on PTRs interaction.
Yeah.
And with dashboards.
So yeah, it's good to definitely investigate, to build an intuition on what cold bars are relevant.
My question is, does cold bar automatically separate the domains like TCBG the ligand?
Not really. No, that's really up to you to define. You can define a cold bar that mixes everything together. It will not complain. They're just atoms to the code.
Okay.
But what you can do definitely is that's where you can leverage VMD really. You can because VMD will provide you atom selection text. If they have different chain IDs, then it will be really easy to say like chain A and something, make that one atom group, chain B and something, make that the other atom group. Anything else? Yes.
I just need some clarification between the hard upper boundary and just upper boundary.
Yes. You know what? That's not something I look into personally. It's just stuff like my first instinct is can you ask Giacomo? Giacomo is not here. It's unfortunate.
It's the other guy's code. So
exactly, it's the other guy's code. And for some reason, so is that related? So maybe is that related to the move to like moving expand grids or something like that? The moving boundaries and
it's like the heart of.
If I see our own doc for that, I will tell you exactly what that means. Yes. You know what? I don't remember really what this does. So I need to have a look at the code and then I'll tell you later on.
Or ask Jacob.
No. Don't tell them. Don't tell them.
just between us.
Exactly. Okay. Anything else? So just to emphasize, since I'm opening this page has a lot of information. So this is again from I navigated there from coldbars.github.io. You have this whole hyperlinked table of contents, and at the end there's an index. It should be an index anyway. Sometimes the index breaks when you compile it. Oh, there's no index. So I need to refresh the index. There will be an index soon. But anyway, there's a table of contents, and then you can just search it. So a lot of information is there. For instance, someone was asking about scripting. You know, scripted, biases. Scripted biases here. It's very short, but should have all the information.
And you guys also have examples in your GitHub page.
And there's examples. So I mean, we can talk about all of these when you get your hands dirty. Yes. Okay. Last question. No last question.
Can you provide your slides?
Yes. Apparently, I will be. It's Joan's job to pester me to provide my slides. So I will provide my slides.
Thank you.
Break time, brother? Break time, Jordan? I'm done. Okay.